Hey, what's up, pre-calculus? Let's go over a few things from Algebra 2 that we will use to proceed with pre-calculus. First is the quadratic formula. Let's remember, if we want to solve a quadratic equation, we could always bust out our favorite little x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And let's remember what imaginary numbers mean. The imaginary unit I is the square root of -1. That does mean I squared is -1. And a complex number is just a number that combines a real value with an imaginary value. All right, fundamental theorem of algebra. This will be important for us. A polynomial function of degree n has exactly n zeros in the complex number system. The degree matches the number of zeros. Linear factorization theorem. This might feel a little new, but if you have some polynomial function with that degree n, well, that function has n linear factors. Linear meaning, of course, we have a power of x to the first. Let's also recall the conjugate zero theorem. I call this the i's come in pairs theorem. You have two i's, your function has two i's. So yeah, if you have a plus bi as a zero of a polynomial, so will its conjugate be a zero, a minus bi. Same two terms, change the sign in the middle. Let's see what we can do with some of that information as we try to create a polynomial function here in number 7 with one of the zeros being -5 minus I root 2. Okay, well, first of all, remember, i's come in pairs, so if -5 minus I root 2 is a zero of this function, well, so is -5 plus I root 2. I's come in pairs, y'all. All right, let's see if we can take these two zeros and write them, use them to write the polynomial as a function of linear factors. Okay, well, okay, all right. We have the zeros here. X equals 5 minus I root 2, and x equals -5 plus I root 2. And we've seen in the past that to change a zero into a factor, we just want to bring all of the terms on one side and have it equal to 0. So we will get this crazy looking factor that we're not used to really seeing things look like this, but welcome to pre-calculus, everybody. You're going to see some new things this year. So we can consider these two to be the factors of the function. So when we go to write the function as a product of linear factors, we would just show multiplying out these two factors. And, you know, again, it looks a little weird, but we have fulfilled the mission. X to the first, both are linear factors, and that would be how to write the function in that form. Okay, well now let's take the next level here and let's see if we can write the polynomial in standard form, which of course means we want to simplify this. So I'd like to show you two methods to get this done, and at the end of this you'll decide which one you're going to be. The first way would be to take those two factors I wrote up above and multiply them out. So this could be a little bit of a process if you think about it, multiplying 3 terms by 3 terms. If you play the distributing game and multiply everybody with everybody, that's going to give you 9 terms. That's not impossible, but it's kind of a lot. What I'd like to point out to you is that the terms we've got take a really special form, and if we can kind of force our terms to fit into that pretty special form, I think it'll be a little bit easier for us to do. So I'd like to remind you about conjugate pairs. Conjugate pairs multiply out two difference of squares. Yeah, conjugate pairs. Again, any two terms, change the sign in the middle, and when you multiply this all out, first, outer, inner, last, the outer and inner products cancel, and of course we just get the difference of squares. What we'd like to try to do is force our parentheses with 3 terms each to kind of fit the format of the conjugate pairs. And if you think about it, they totally can. I will just chunk together the x plus 5s and call that the first term, kind of like the a, and I will leave the I root 2 and negative I root 2 out as the b term. So if we were to multiply this as the difference of squares, oh my goodness, we'd get x plus 5 squared minus I root 2 squared. That seems a whole lot more pleasant than multiplying 9 things out. Because this we could get through pretty shortly. Either write it out twice, x plus 5, and you can FOIL that. That wasn't so bad. And then over here, we've just got to take some really special care to make sure we square this appropriately. So I squared will be I squared, and root 2 squared will be 2. So let's figure out what's going on here. We're minusing I squared times 2. Well, I squared is negative 1. So negative 1 times 2 is negative 2. We're subtracting negative 2. So we are adding a 2. And let's just combine the like terms. Attach a little f of x action to this. And we've got the standard form of our function, and if we were to set that equal to 0 and solve, we would get the 2 zeros listed above. Beautiful. Okay, the other way we can look at this is to complete the square backwards. So let's take the 2 zeros and realize we can write them separately. We could also write them with the plus minus shortcut, expressing 2 numbers just in one kind of notation. And what we want to do, like I said, we're going to complete the square backwards. So why don't we isolate the plus minus? So I'll add a 5 to both sides. And then we can just square both sides of the equation here. And, you know, think about that. I know we're squaring 2 numbers at once, but whether you square positive or negative I root 2, I'll just play that out right here. I root 2, that would give you I squared times 2, which is negative 2. And if you were to square negative I root 2, that would mean, of course, you're writing that twice and multiplying it. Negative I times negative I is still positive I squared times the 2, still comes out to a negative 2. So we're not losing anything here. We will get a negative 2 no matter how we play that out. And if we simply now add the 2 to both sides and maybe attach, again, just some kind of beautiful little function notation with this, you do see we get the same exact function as before. So both ideas are pretty similar. They both involve squaring an x plus 5. Here and here we did that. They both involve squaring I root 2. It's just, you know, a slightly different approach. However you want to think about it is valid. Okay, let's see what the next problem entails. And as we take a look at it, we are trying to write a degree 4 polynomial function. Don't forget the f of x at the end. And we're going to try to create it to have the zeros negative 3i, positive 3i, and then 5 halves with a multiplicity of 2. So I've listed the 3 distinct numbers there, and we can turn them into factors by doing what we've been doing here, collecting them on one side of the equation with an equal 0. And for the factor 5 halves, we'd like to clear out the fraction and then subtract. So that gives us a 2x minus 5. All right, let's write out the function here now, like we are supposed to do as a product of linear factors. And we've got to not forget about that multiplicity of 2. I will show that the factor 2x minus 5 appears 2 times. So that is the linear factor of factorization of that function. Again, each of the x's is only raised to the power of 1 within each factor. Okay, let's write this in standard form, and of course we still must always know standard form means simplified form. Okay, so we've got a little algebra 1 multiplying that we've got to take care of here. I'll start you off and then leave you to try some on your own. What I would really encourage right here, though, is to notice again those who are staring at a pair of conjugates. And let's remember the shortcut, conjugate pairs, multiply out two difference of squares. So we can clean that up momentarily, but right now I'll just leave it as x squared minus 9i, and we can square the 2x minus 5. Again, you could write it out twice and bust out your favorite four-letter F word in FOIL. For those of you that are kind of getting used to foiling in your head or busting out the square, double product square shortcut, that certainly saves a couple moments of your life. Okay, we're getting closer and closer here to getting it simplified. Just rewrote I squared as -1, so -9 times -1 becomes x squared plus 9. Why don't you pause that out and multiply these two together? Okay, welcome back. Let's take a look at how that played out. Excuse me, Rob. And when you multiply those terms all together and combine them, hopefully you've gotten something pretty similar looking to what I've shown you here. Okay, one more example. Let's go. Work on finding the zeros of this function here, a little quadratic function. This will give us a chance to review some other methods besides factoring that we can use to solve a quadratic equation. I'm going to show you how to complete the square, which you learned in algebras 1 and 2, and then we'll also work it out with the quadratic formula. All right, completing the square I think is very lovely for this problem. If you notice, a couple great things work in our favor. The x squared is what I'd call naked, no coefficient, and the x term is even. That is very, very awesome for us. Oh, whoopsie. That's a little better. X squared plus 8x plus 19. Okay, completing the square here. We want to cause a perfect square trinomial on the left-hand side of the equal sign. We are basically setting something up for Inga to devour. So if you remember from Algebra 2, we're going to take that x value, the x term of 8, cut it in half, get a 4, and then square it. And we want to add 16 to both sides of the equal sign. Why? Well, look at how this one factors here. X plus 4, or x plus 4 squared. And then over here, combine those two values and we get a -3. Okay, Inga, here we go. See if I can freak out my cat. Square, square. Don't forget the plus or minus. Yeah. You can't see it, but my cat just stared at me as if to say, "What are you doing over there, lady?" Anyway, the square and the square root, of course, cancel. Square root of -3 is plus or minus I root 3, and if we get the 4 by itself, we do get the two zeros of that function. You can write them combo deal with the -4 plus or minus I root 3. You can write them individually. Nobody is going to really bother you about which way you do it. All right, let's just squeeze in some quadratic formula, and same problem, we should get the same answers. I'd like to compute the discriminant first. That's the value under the radical. That's where all the mistakes tend to happen. So I'm going to figure out 64 minus 76 to get a -12. That's the value under the radical. All right, so let's now see what we've got. X equals -b, so -8 plus or minus square root -12 all over 2 times the a value of 1, or just 2. Could I please recommend, oh, there she goes. Okay, guest appearance. Could I please recommend we split this fraction up and then simplify it? You will surely not make any errors if you try it out that way. All right, so that should give us -4 plus or minus. Let's think of root 12. That would be -4 times 3, so 2i root 3 all over 2. And when we simplify, look at what we get, everybody. The same 2 zeros we got before. Yay! So no matter which way you do it, you're going to get those as your solutions. Okay, everyone, that's enough for now. Ta-ta!